Hello class again and welcome to this particular video, and in here we're going to be exploring another type of the position time graph. In this case we're looking at curved position time graph, and you're wondering what are curved position time graphs and how is this different from what we talked about on our previous video. On our previous video we talked about pretty much variations of the position time graph that involves straight lines, either some that are in this case where we have our time in seconds and we have our position which is measured in meters, and we had a direction of course which is pointing east. We had different variations. In this case we had one that is increasing, and we have a specific constant velocity with zero acceleration, and another case scenario is when it has a decreasing slope. This shows in this case that we still have a velocity constant but our acceleration is zero. And we had other ones where we had the horizontal slopes. In this particular case we have a static object in the east direction and there is no velocity, however as well no acceleration. And we also looked at how all these guys are located below the graphs as well. But in this particular video here we're going to be looking at variations of a curved position time graph, and the curved position time graph involves accelerating objects. Take note of that. So objects that have changing velocities, and as a result of that leads to a particular result which is accelerating objects. And this comes in variations, and accelerating objects comes in variations based on how the curve positions look like. And so in here we're going to look at a couple of things in changing velocities. We're not only going to look at the position time graph, we're also going to look at the velocity average or average velocity time graph. And finally we're going to see how this connects to the acceleration time graph. And so first off is we're going to look at two case scenarios, but in those two case scenarios we're going to be looking at two for each. So first off we have case scenario number one, and case scenario number one shows you a specific position time graph, and the position time graph here in this particular case has our particular position located in the east, and in here it is measured in meters and our time is measured in seconds. So case number one is when you have a curve that is changing and it is curved up and it is showing this particular interesting pattern. And so this pattern here is known to be a curve, and this curve here is case number one, which is going to be represented as A. And another case scenario here is when we have a different object and it is curving down in this particular manner, and so this here is going to be represented as curve B. So take note that our position is now looking at it in terms of negative values of our position with respect to time. So as a result of our position time graph, we're going to be comparing these two and observing what is happening right here. So what you notice is that when you take the instantaneous, take that of that instantaneous velocity, we are trying our best to figure out what the slope at each point of this graph is. And so what we notice is by going from this region here to the next, we take our instantaneous rate at each point on this graph, and we see that the line of our instantaneous velocity at each time is increasing, and so an increasing slope as we go from time 0 to time, let's say, infinity. We actually have our velocity time graph where we have our V average with respect to time in seconds for our A to be showing a particular positive slope that is pointing up. And so therefore, as a result, we are having change in the velocity. And once we have that happening, this results in our acceleration to be constant. And so therefore our acceleration time graph in this case, where a with respect to our time, take note of this and note that our acceleration is also in the east direction. And finally here we have our units to be in meters per second squared, and this velocity as well is measured in meter per second, but our unit is with respect to the direction, which is east. And so therefore our acceleration for A is shown to be at this particular position right over here. Let's use orange for consistency purposes. And so therefore here is our acceleration for A. Now how about RB? Let's analyze RB. And what we see for RB is that when you perform the instantaneous velocity of RB, we see that the slope is going steeper, but it is negative. And so when you have negative slopes and it is increasing, we have our particular velocity time graph for our curve B in position A going into velocity time graph to show a particular curve, a line that is downward. And so a negative slope for our B on our velocity time graph results in our accelerating object to be constant, in this case in the negative region of our acceleration time graph. So if we take the slope of this line here, that gives us a constant acceleration. So that means we have an accelerating object. So this is one case scenario over here. This case scenario looks at a particular K pattern where the first K is showing a really steep increase in the velocity, how the other side it has an object that is kind of kicked at a particular height and it is going downhill. So therefore we see that the object is accelerating based on the velocity changing, and it is accelerating in the negative direction. And so this is applicable to objects that is falling down based on gravity impact, as is shown here. And this is also shown when an object is going from a particular curved hill and it is trying to slide down, just similar a little bit to skiing a little bit. So it's kind of interesting to see how this pattern is applicable in this sense. And now looking at a different case scenario where we have objects that is almost similar to what we have here, but in this case looking at the position time graph, where in this case we have our time in seconds and we have our position right over here, and we have our same unit, which is in this case meters pointing east. But here we have a specific pattern and it shows that we have an object going down. This is similar as well to what we have for our B in here. And so our B in here, but in this case for our D, we're having this situation occurring, but now it is happening in the east direction. And while this right here, another pattern here, which is in this case C, is going to be increasing, but it is in the west direction for our position. And so this is going to be our C, and this here curve is going to be our D. And so therefore when you perform the same thing here like what we did looking at the instantaneous velocity of each point on curve D, what we notice is that we observe that there is also a negative increase in our instantaneous velocity. Therefore the instantaneous velocity or tangent to the curve is increasing, but it is a negative value. So therefore when we perform our velocity time graph for that particular curve, we have the same thing happening in here for our specific D, but it's also applicable to now our D. So pretty much B and D are exactly the same pattern that we're going to see over here. And so when we do the same thing now that we did for D in see by checking for the instantaneous velocity and see what is happening as we go from here to there. We see that the curve is increasing at a particular positive velocity, and so this curve showing that the velocities are increasing based on the instantaneous velocity shows that the C pattern of our instantaneous velocity is the same as that of our A. Therefore, our velocity time graph for our C is going to look like what we have for A. So once we have this taken care of, we can then conclude that objects that are in the positive region but showing the quick steepness that increases in terms of the curve will show the same pattern of our velocity time graph positioned in the positive direction on the first quadrant. However, looking at the other way around, where you have curve that looks like it is downhill but it is increasing in the negative instantaneous velocity, but in this case one is in the first quadrant but the other one is in the fourth quadrant, we're going to have a velocity time graph to show that both of them will have negative slopes at the fourth quadrant in our velocity time graph. And as a result of that, our acceleration time graph of our A will be exactly the same as our C as shown in here, while our particular B will show the same slope based on our acceleration with respect to our specific D, which is shown right over here. So this is really interesting to play around with in terms of how all these particular patterns are shown here, and we can actually go back. We can go back, and to go back, all we have to do is go from our specific slope, which is our acceleration line, to the velocity time graph by performing our acceleration. By performing our area. So by performing area of our particular curve, we'll be able to go to our velocity time graph, and from our velocity time graph to our displacement or position time graph, we'll also be able to do the area under the curve on our velocity time graph to get to our position. And on the other hand, when you're going from our position time graph to our velocity time graph, you do the slope of the line, and vice versa in this particular case, from our velocity time graph to our acceleration time graph, like what we did, we perform the slope. So that's about it for this particular long video. I hope you found this really informative. Please let me hear your thoughts. By that way, I can talk to you soon. We'll explore some other questions in terms of application. All the same, stay smart as always and believe in yourselves.